2 times the oscillator has a position of 2 centimeters. So we pull the mass down by 5 centimeters, then we release it. So we know the mass is going to come back up above equilibrium. It'll hit 2 centimeters, come up to the amplitude, and then swing back down, hit 2 centimeters again. Those are the 2 times we're trying to find. To try and sort that out, what those times are, let's use our equation for position. So from part D, we know the equation for position is given. Let's plug in our 2 centimeters for x. So x of t equals 5 centimeters times cosine 8.78 times t plus pi. We know that our x is 2 centimeters. So 2 centimeters equals 5 centimeters cosine 8.78 t plus pi radians. Divide both sides by 5. 2 centimeters over 5 centimeters, that gives us 0.4, is equal to the cosine of 8.78 t plus pi. To figure out our time, we have to get rid of our cosine. We do that by taking the inverse cosine of both sides. The inverse cos of a cos just leaves you with the argument. 8.78 t plus pi equals the inverse cosine of 0.4. Okay, so our first step is let's just do this on our calculator and let's solve for t. So let's see what that gives us. So when we go to our calculator, the inverse cosine of 0.4, make sure your calculator is in radians mode. Inverse cosine 0.4 gives 1.16. Let's put that in our equation and solve for t. So 8.78 times t plus pi equals 1.16. T equals 1.16 minus pi divided by 8.78 gives us negative, because pi is 3.14, 0.226. That's before we start the whole oscillation. That's before we start our stopwatch, so that can't be right. So let's take stock of what we did just so we can get an idea of where to go next. What we did when we did the inverse cosine was we figured out what angle, when we hit cosine, does it give us 0.4? And the answer is this angle right here. We have to ask, is that the only angle? And the answer is no, that's not the only angle. The angle down in the fourth quadrant also has the same value. So let's think about that one next. So let's draw the picture over here. The angle down here, where that amount is 1.16, is also going to have the same value for cosine. Now, if we take the angle at minus 1.16, put in a negative here, we're going to get a bigger negative time, so that can't be the right angle. So what could be the right angle? I would say that this one could be the right angle. So that's 3/4 of the way around plus this much, or it's 2 pi, take away that much. So the inverse cosine of 0.4 can also be 2 pi minus 1.16. And we can try that on our calculator if we wish, just to double check it. So we'll do 2 times pi minus 1.16. Let's do the cosine of this angle and see, do we get 0.4? We do indeed. Okay, so let's plug this in and find our time. 8.78 t plus pi equals 2 pi minus 1.16. Solve that for our time t and we get positive 0.226 seconds. Okay, so now this is our first time. This is t1. Now we have to find our next time. So let's go around the unit circle some more. So our first angle was we started at 0, came up to the angle in this quadrant. Our next angle was we came to the angle in this quadrant. So now for our next time, we've got to go back to the angle in this quadrant and ask, if we're not going to call it 1.16, what will we call it? So to get to the angle in this quadrant, we can come all the way around the circle and back up to it. So that angle could be 2 pi plus 1.16. And these are some trig identities that you might learn in a math course in high school somewhere along the way. So now let's put this in and solve for t here. 8.78 plus pi equals 2 pi plus 1.16. Solve that for time, and we get a time value of 0.490 seconds. And this would be our second time. So there are the two times at which the oscillator has position of 2 centimeters. And the hard part here is figuring out what am I going to do with the inverse cosine and thinking about that unit circle and the fact that cosine has multiple values. Okay, the last part of the problem says find the velocity of the oscillator at those two times. So let's see about doing that part. Let's get the equation for velocity first. So part F, our position equation is x of t equals a times cosine omega t plus phi naught. Our velocity equation is the derivative of position. So to take our derivative, our constant comes out front. The derivative of cosine is minus sine. And then to finish our chain rule, we have to do the derivative of what's inside. The derivative of omega t plus phi naught is omega. So our equation for velocity is v of t equals minus a omega sine omega t plus phi naught. So to find our velocity at those times, we'll just use our equation and plug in our times. So velocity at t1 is equal to minus the amplitude, 5 centimeters, times omega, which was 8.78 seconds to the minus 1. We found that in part B, times the sine of omega, 8.78 seconds to the minus 1, times our t1, 0.226 seconds, plus pi. Put that through the calculator, and we get for our velocity plus 40 centimeters per second. Okay, and that one makes sense because for our first velocity, it starts down here and it moves upwards. It's moving up. We expected a positive velocity. Okay, so you might have a thought about what the second velocity is going to be. Velocity of t2 is equal to minus amplitude times omega times the sine of omega times t2, and our t2 was 0.490, plus our phase constant. Put that through the calculator and we get negative 40 centimeters per second. Okay, negative makes sense here because our oscillation goes up, then comes back down, moving in the downward direction, we get a negative velocity.